Let us study an important phenomenon in radioactivity, that is simultaneous decay modes of a radioactive element. Sometimes it happens that if there is a radioactive element X, it transforms to element Y, which is the daughter nucleus, as well as there is a probability that it may transform to Z, which is another daughter nucleus. That means the nuclei of X may decay to Y or it may decay to Z depending on the probabilities in which it can decay into two different daughter nuclei. And such kind of phenomena we call simultaneous decay modes of a radioactive element. And randomly any nuclei can be transformed to Y or to Z depending on the probability of decay. Say if X decays to element Y with a decay constant lambda 1 and X decays to element Z with a decay constant lambda 2. Suddenly if lambda 1 is more than lambda 2, then the probability of disintegration of X to Y will be more because it is making the nuclei more stable. And a high value of lambda implies higher stability. So if lambda 1 is high, we can say X will be more unstable for its decay to Y compared to decay to Z. Now in such situations we can write when a radioactive element has probability of more than one decay, then its effective decay constant can be given as, this is written as lambda effective and its value is lambda 1 plus lambda 2, and here lambda effective is the decay constant with which X is disintegrating. Similarly, we can write if probability of disintegration of X to Y or Z are P1 and P2, then we can use lambda 1, which is the decay constant for X for its disintegration to element Y. This is written as P1 multiplied by lambda effective, and lambda 2, which is the decay constant of X towards disintegration to Z. This is written as P2 multiplied by lambda effective. This is the way if overall decay constant of X is given, or we can say if half-life of X is T, this implies here the value of lambda effective will be ln 2 by T. And using lambda effective, we can find the individual decay constants of X, disintegration towards Y or disintegration towards Z. Let's continue the same on the next sheet. As we have studied here that if a radioactive element X has a probability of decay to two elements Y and Z with decay constant lambda 1 and lambda 2, analytically here we can write if at T equals to 0, there are N0 nuclei of X, then after time T, number of nuclei left are, this can be directly given by radioactive decay law as N is equals to N0 e to power minus lambda T, and the decay constant for the element X here we can write as lambda 1 plus lambda 2 into T. This is the relation we use for number of parent nuclei left after time T if initial number of nuclei were N0. And here we can directly write the rate of production of nuclei of Y is the rate at which Y is being produced is the activity of X towards Y, and this rate of production of Y we can write as lambda 1 N. Thus we are talking at time T. One number of available X nuclei are N. Similarly, we can write here rate of production of nuclei of Z is, the rate at which Z are produced will be lambda 2, and this is the activity of X toward Y as well as Z, which are giving us the rate at which Y and Z nuclei are being produced.